Yeah, and you can get some that are a little bit, like you've got that one in your back pocket now, so you can get some that are a little bit more out there. More application driven if you want, or if you're having fun just looking at the OChem, strictly OChem stuff, then go with it.
Yeah. So I've been trying to find some stuff that was like more biochemistry related, but could have OChem mechanism stuff in there.
It's hard, but yeah, because all the mechanisms in biochem are all enzyme catalyzed for the most part.
Yeah.
So. All right, well, we'll go ahead and get started then. And then just for clarification, so your first assignment for the journal article presentation is pick 4 possibilities like we talked about on Tuesday. Then next week, basically just meet with me one-on-one. And we'll just narrow it down to 1. And then the week after that, you're gonna present it. So it'll just be, you can use PowerPoint if you want, you can use, whatever presentation software you want. But basically you're just gonna walk us through the article, and be the expert in the room. So it might take some time to really get a handle on some of these papers. But that's why it's the final project. And then the week after that will be finals week. Which I think is either, and our finals either Tuesday or Thursday, I don't remember which.
All right.
But
So
we're
is this
closing on it.
is this the last chapter that we're gonna be going over, or is there?
Probably. So this is week 9. Week 10 is the last week to do new material, really, because week 11 we usually keep for at least one of those lectures as a review.
Right.
So we'll see how this one goes. It turns out that alpha carbon reactions they show up all over the place, but they're all fairly similar in a lot of ways. And so we might have time to do like a special topics lecture or something.
All right.
Depending on how things go. But this is the last big topic. So this is just our review that we used the other day, our roadmap for getting around the different acid derivatives. Just as a review, maybe a little smaller so it fits on the screen. Ish. And really this is kind of what I would use to study. This is a really good reaction review of that whole chapter, 2 chapters, I think it is actually. I just want to make sure that was in there so that you have it on the PDFs if you hadn't seen it yet. So a quick review of our intro to alpha carbons. So, and they use this terminology with a lot of different functional groups. But like we saw back in fault order, there's a little bit of inconsistency with what they designate as the alpha carbon. With carbonyls, it's really clearly defined as you've got your functional group and then 1 carbon away is the alpha carbon. And that's typically what I see more often. Occasionally you'll see things where they say the alpha carbon is the carbon with the functional group on it, but not when it comes to carbonyls. So it's really consistent when it comes to carbonyls. And we will see some, I think where we saw it before is when we talked about alpha beta unsaturated compounds. So the reason that these are of particular interest is because of resonance and because of that phenol form that we can get with these carbonyls. We see a difference in the reactivity, because if it's in its enol form, then it can react like a alkene, right? And so we really do see, but it's not even just strictly like an alkene, because we do have a polar alkene bond, really, mostly due to this electronegativity, the oxygen. And so, and we're gonna see that most of our alpha carbon reactions go through an enol or an enolate. An enolate is basically just a deprotonated enol. And so if you have a deprotonated enol with a negative charge, that's still relatively stable because we've got this resonance structure. And so those happen to be the two most common intermediates that we see here. So again, we've seen these enols before, but it's been a while, so. Here's a review of the mechanism. And to be completely honest, I'm not sure exactly what makes it a tautomerization versus an isomerization. Maybe just that it's an equilibrium process, because in biochemistry, if we have a reaction where we go from one isomer to a different isomer, constitutional isomer or otherwise, we call it an isomerization reaction. But for whatever reason, in this particular case, they call it a tautomerization. So my guess is that it's an ongoing equilibrium process, is what makes it a tautomer. I'll look that up at break to double check that. And there are some other factors that go into it. So we looked at cyclohexanone versus the enol form. It favors cyclohexanone 99.99% of the time. You're going to find it in the ketone form. However, if you have a diketone on the beta carbon, because we get some extra stabilization of that hydrogen, we actually favor the enol form in that case. Also because that gives us resonance. So between the resonance and the extra intramolecular force, I suppose at that point, stabilizing it. So we can see it's kind of a wide range, and it depends on a lot on the environment, the rest of the molecule, what form we favor. Right, and so it's a pretty simple mechanism, and it can be catalyzed either by acid or base. But just like with our carboxylic acid derivatives, we just need to make sure we do our proton transfers to the right order. We can't make, if it's acid catalyzed, we're not going to make anything negatively charged at any point along the way. And if it's base catalyzed, we're not going to make anything positively charged along the way. So acid catalyzed, first step is protonate your carbonyl, very similar to what we saw with the carboxylic acid derivatives. And then there's going to be a resonance structure that goes back and forth between the carbonyl, protonated carbonyl versus a carbocation. Which of those would be the major contributor in terms of resonance? Which would we expect to be more stable? That's always the first guess, but remember that a carbocation has what property? Carbocation always has an incomplete valence. Yeah. Even though this puts a positive charge on an oxygen, everything still has a full valence.
Right.
And that's the bigger factor here, so this is the minor contributor, but it is a significant enough contributor that we can see it go through an elimination reaction. So it's effectively like a resonance stabilized E2. So instead of having a leaving group leave, you break up the pi bond or the carbon's valence by breaking a pi bond instead of having a leaving group leave. And then we just need anything that can act as a base can pull that hydrogen off.
Yeah.
So before I show you the base catalyzed version, you two try and draw it on your papers. Think about the order of these steps and just make sure that you're not making anything with a positive charge. Find the pollen season.
Seems less steps.
We see that a lot. The base catalyzed versions tends to have fewer steps because there's fewer protons to move around.
Yeah.
In this case, if it's base catalyzed, you start by making a carbanion.
Yeah.
So you pull that hydrogen off first.
I kind of consolidated the two steps into one with Andrew. Would that be okay or the test? It should be like.
It's better to think about it as being two steps because you are gonna have, if you do it as one step, it's hard to see that resonance structure.
Okay.
Because you really are gonna see a significant. And in this case, we can go with your first instinct when it comes to which of these is the major contributor. Because everything has a full valence in both cases, right?
Yeah.
So the major contributor in this case will be the one that puts the negative charge on the oxygen. Because the oxygen's more electronegative.
Right.
And then we can just do. Proton transfer to get us the enol. So really it's the same two steps, just in opposite order. And the difference is the other significant difference that your resonance structures have opposite charges. A resonance structure when it's acid catalyzed has a positive charge, a resonance structure when it's base catalyzed has a negative charge. Right, there's prettier version. Deprotonate, resonance stabilized anion. And then protonate. Occasionally, you can have cases where these steps happen within the same molecule. If you happen to have a proton source that's close to the other reactive group. For instance, in this case, it's actually pretty easy to do proton transfer, but within the same molecule. And then just, so you actually have kind of like an ongoing resonance structure here, because if you transfer the hydrogen over here, and then those electrons move over and those electrons move over, and these electrons stay there, you actually get the same molecule. Basically just where with the carbonyl and the alkene reversed. All you have to do that is a one-step transition, and then some, it's almost like, it's not quite a resonance structure because you are breaking a sigma bond, but then the rest of the electron movement is all just happening simultaneously.
In this case, would like since the hydrogen nucleus is just one proton, would it be small enough to be subject to like quantum effects where it's in some like weird superposition and like both oxygens, or is it like a proton too big for that?
Protons are for the most part too big. There's some small amount of that. You can see some, I don't think that we see something as large as a proton tunneling, but it is gonna be kind of, there's probably gonna be like an equilibrium state where it's kind of halfway in between instead of closer to one versus the other.
Right, just as
It's constantly shuttling back and forth. But I mean, just the protons are about 1,800 times larger than an electron by mass.
right.
And you really do need to get down into the electron level to see the quantum effects be really significant. And if we wanted to draw that resonance structure, or what it would actually look like. Basically, you're gonna have that. All of those happening at the same time. Right, because the only one that's the slowest step here is gonna be the proton moving. Everything else is just electron movement. And in all cases, these electrons are moving towards a carbon that is full for a second, but then those electrons move over this way, and these make room for that. These electrons move up, which keeps this oxygen neutral.
That's cool though, it's like ends up being so cyclic.
It is, it's one of the reasons why we had that whole chapter on electrocyclic reactions.
Yeah.
This technically, it's not a cycle addition,
Right.
but it's just a rearrangement is all, but it's similar to those rearrangements that we saw.
Yeah.
Where we actually keep the same number of sigma bonds before and after. We just looked at it predominantly from the alkene standpoint, but this is another example of that same thing. All right, so as far as how we can expect these to react, we actually look at the electron density of an enol. We actually see a partial positive, or sorry, a partial negative on the alpha carbon. And really, this is a, so once you make the enol, so that's why it's not symmetrical here, this is the enol form. We would expect the electron density to be symmetrical when it's in the ketone form. Right, because both of these are gonna be CH3s. But once we put it in the enol form, whichever carbon gets the alkene bond has actually half of the that carbon is electron rich. We would expect maybe that it was missing electrons if we just thought about it in terms of induction, in terms of electronegativity. But we actually see extra electrons, not missing electrons. So starting from the enol form, is there a resonance structure that accounts for, could account for that?
Yeah, you put the positive charge on the oxygen and then a negative charge on the carbon.
Yeah, so that's gonna look like those electrons move down, those electrons move over, right?
Yeah.
Then we have a protonated carbonyl with a positive charge and a carbanion at the same time. Going from something that's totally neutral to something where you have a positive charge on the oxygen and a negative charge on the carbon, we wouldn't expect this to be the major contributor, but it is a contributor.
Which is enough to like offset the electron density by quite a bit, it looks like.
Yeah, pretty similar. I mean, we could actually put numbers to it if we actually ran the calculations.
Yeah.
One of the calculations you can do with Hartree-Fock and with DFT is actually, turns out that if you take all of the orbitals, all of the wave functions of all the orbitals, and you square them and add them up, you get an overall electron density.
Okay.
And so that's where these electrostatic maps come from, is basically taking that wave function that we calculate in games and just, it's a weird, the wave function itself, the orbital function itself is not electron density, but if you square it, it is.
Oh, interesting.
Because the wave function takes into account destructive interference. And you get those out of phase. But when you square it, the out of phase part goes away.
Yeah.
So, and then if you sum up all of the orbitals squared, you get this. Yeah, and it does, so we could actually get a number for the dipole moment here, exactly how positive this or how negative this partial negative is, but it's significant. I mean, even if this is a 10-to-1 ratio, that's still a tenth of a negative charge. Or you can think of it a tenth of the time, on average, you have a negative charge.
Ketone, it will go through the tautomerization, like in this case, both of the methyl groups. And so this is just kind of like when it does it with one, that is temporarily what the electron cloud looks like, right?
Right.
Okay.
And because the tautomerization involves breaking sigma bonds,
Yeah,
that's not a quantum superposition.
right, because that's like a slow process.
That's a slow process. And so what you have is you have an equilibrium reaction to make this enol,
Yeah,
and then you'll also have an equilibrium reaction to make
right,
this enol, which it's a symmetrical molecule,
yeah,
6-to-1 doesn't make a difference. If it's an asymmetric molecule, you have to take into account that you have two distinct alpha carbons.
right, so like one of them was an ethyl, that would obviously react differently.
Exactly. If one was an ethyl, which of these enols would we expect to be more common?
The methyl, right, because the electron donating. group
Yeah.
of methyl.
If this is gonna have a partial negative on it, then having an electron donating group attached to it's not gonna be very helpful. Right, so having the electron donating, you would expect to see less of this, more of this form. But as long as it's symmetrical, we don't care about that. And this is also, now we're getting into the nitty-gritty about why chemists are so picky about the way you draw arrows. Because that means something totally different than that.
Yeah.
Right, the resonance structure versus equilibrium have very different properties.
Right, since movement of proton basically versus movement of general.
Right, and the movement of the electrons don't happen simultaneously.
Yeah.
Well, not happening simultaneously, it's a quantum superposition of both of these states. Right, and that's exactly what we heard, right?
It's like your wrist. It's like your wrist. Your wrist.
Oh, that was middle school's here again today. Mariola's husband works at the middle school. I just saw him walk by. He used to work at the school, at the elementary school. My kids go to school, so I saw him all the time.
Middle school was the absolute worst. Hormones are raging, everyone's absolutely.
And nobody can handle it. Yeah. I'm feeling all these feelings. I've never felt these feelings before. I don't know what to do. I just remember there was like a beloved seventh grade teacher that I had in seventh grade for half my classes. And she left unexpectedly, like 2 weeks into the school year. And they hired a teacher straight out of college, like just finished her. And she taught kindergarten for her student teaching. Then they threw her into a classroom of seventh graders, and it was just awful. I don't remember doing anything myself that made her cry specifically, but like 3 times a week, the entire year before we was crying.
Yes, cruel and unusual.
Yeah, I think they gave her kindergarten after that, I think, to make up for it.
Makes sense. Middle school was the era when I got one of those fake black leather belts with the metal like studs.
Oh, yeah.
That's how you know it was bad.
That was the time and place, right?
Well, this Hot Topic was a thing.
Hot Topic. So I saw a meme about Hot Topic the other day. I want to see a Romeo and Juliet story, except it's an employee at Hot Topic and an employee at Pakistan.
That's amazing.
Because you kind of sorted, because that was the middle school sorting hat in the early 2000s. You were Pakistan or you were Hot Topic.
Absolute emo or like board shorts.
Yeah, exactly. Anyway. All right, let's start with 3-methyl-2-butanone. And that's an asymmetric molecule. So let's draw both enols and draw a mechanism for at least one of them. Might not show both of them under base catalyzed conditions. Today. So first step first. We're making this enol, we're gonna see. That has. Its resonance structure.
Kidding, go to college, it's awesome. I've never had more fun.
Which, if we're really under base, if it says specifically. Show the enol, we do wanna see that last proton transfer step. But really, we're under basic conditions, we probably actually have the enolate rather than the enol. So leaving it like this would actually, before it says show the formation of the enolate, we stop right here. And this is one of the keys with alpha carbon chemistry, is the fact that we can just use hydroxide to pull a hydrogen off of a carbon is pretty unique. Right, usually we think of carbon hydrogen bonds, they're not acidic under normal circumstances, right? It's just the fact that it's an alpha carbon to a carbonyl that allows us to do this, that makes them acidic. They're not as acidic as a carboxylic acid, but they've got a pKa that's definitely less than hydroxide. And there are other enol that we could make. It's gonna look like that. And we would expect
That one would be less favorable.
less vapor. The other way you can think about it is that this resonance structure, carbanions follow the exact opposite rules of stability as carbocations. Carbocations, the tertiary would be more stable. Carbanions, the primary is more stable.
Which now in terms of thinking of like methyl groups as electron donating, that makes a ton of sense.
Exactly, we're laying the groundwork for this all year.
Yeah. In terms of radicals follow the carbocations for stability, right?
Radicals and carbocations are most similar, they both have an incomplete valence.
Right. So it's that they want more because of the valence.
Yeah, right, and so the electron donating stabilizes them.
Yeah.
Carbanions have a full valence.
Yeah, this was today's specific lecture, make a reminder about valence system, those perceived resonance as far as stability.
Exactly. That's why we always keep coming back to it.
Yeah.
When you can see also why, I know I harped on this before, but why OCHEM gets such a bad rap. And I'll make a generalization, among biologists that have to take OCHEM.
Med students, you'd say.
Med students. Because you can't memorize your way through this and have it make any sort of sense. It's like memorizing gibberish, which of course that's gonna be difficult unless you're willing to put in work to change how you think about these.
Like, I just understand.
Right.
Yeah.
And again, and engineers hate it too, because you can't just math your way through
No, it's just because they're lazy like the rest of the generation.
it. You just lump engineers into one generation.
No, it's just my favorite insult, it's
Like the rest of the configuration, yeah. I like that, but I have to be careful with that because people will take me at my word instead of seeing the sarcasm
No,
there.
no, that's why, like, we get one in the room, we're all on the same page at this point. Yeah, I have to start being careful between one and start teaching here.
It's true, yeah.
It might be a. Outside though.
All right. One more concept before we take our break. These enolates have two different places where you can put the negative charge. Obviously, we would expect to see the negative charge more often on the oxygen, like we mentioned. So this would be a major contributor, but both of those are contributors. Which means that they're what are called ambidentate. Meaning that you can attack from two positions. Either the oxygen can act as a nucleophile or the carbon can act as a nucleophile. If you're trying to work out the etymology, dentate, same root as dental, teeth. You can bite it from both ends. And if you think back to Gary, I know that we talked about coordination compounds last year.
Yeah.
That's the same terminology used, right? So I'm not sure, David, if you remember your Gen Chem where we, if you talked about coordination compounds like EDTA or making those complex ions.
Yeah, it's rattling around.
We called those, if you had something that could attach in more than one place, we called that bidentate.
Okay.
So that means it actually attacks it from both.
Yeah,
Ambi means either.
yeah,
Right. So it's a slight difference because if you had something like ethylene diamine looks like, oops, one more carbon in there. Looks like this. This one winds up being bidentate as opposed to ambidentate because it can attach to both ends at the same time. Ambidentate means you have to pick one or the other, but it could be either of them, as opposed to a polydentate like this.
there's a lot of proteins like active sites.
Exactly, they tend to bind in more than one place because that's how you get the orientation right. And then EDTA, which we've talked about as a treatment for heavy metal poisoning. I think we've talked about that in this class, right?
Like chromium.
Like chromium. EDTA is ethylene diamine tetraacetic acid. So it's if you attach an acetyl group, two acetyl groups to each of those nitrogens.
Okay.
So you get CH2 nitrogen, CH2 and then the same on the other side. So you wind up with a lone pair on each nitrogen that can attack.
Yeah,
And then each of these acetic acid groups can also attach.
right.
So it's actually a hexadentate ligand. You can actually surround the entire heavy metal ion
Oh, wow.
with one molecule if you do it with EDTA.
And then it precipitates out.
And then it stays water soluble
Oh, okay.
as opposed to being bound to a protein.
Yeah.
Because most heavy metal toxicity comes because a heavy metal ion displaces another metal in your enzymes. And so it just sits where that other metal is supposed to sit, but it doesn't react the same way.
Okay, so that just prevents it from being able to.
It just keeps it water soluble so that your urinary system can flush it.
Takes the affinity for the protein because
Exactly.
It has a higher affinity for this.
If you use EDTA and you don't have heavy metal, it actually has its preferences as opposed to what metals it attaches to more,
Right, size wise.
size and just charge.
Yeah.
But it'll actually pull most metals out, so you can actually make yourself anemic.
Yeah.
If you do that, because it'll also pull iron out of your hemoglobin as well. It'll react more with bigger heavy metals like lead and mercury. But if you don't have those around, or if you stay on this regimen for too long, even if you have really bad heavy metal poisoning, they'll usually do like a course of EDTA treatment and then give you a week break to replenish all the ions that you're supposed to have. Anyway, a little aside, since we're using similar terminology. Alright, and then what that actually looks like as far as acting as a nucleophile. So if you have anything with a positive charge, you can have your oxygen come over and attach, or you can have your carbon come over and attach. And this is sort of a tricky one to predict what's going to be favored. It's definitely a case of kinetic versus thermodynamic products. Because for the most part, coming up with a product, let's say once we attach our oxygen to the electrophile and we still have this alkene group here, the oxygen is the more common, or is the major contributor to major resonance contributor here. So it's a stronger partial negative on the oxygen, which makes it a better nucleophile. But we're generally speaking, an oxygen bond to something else is less stable than a carbonyl core. So
That's kinetic.
so this is the kinetic approach. But the carbon attacking is gonna give us the thermodynamic product.
Yeah.
Because let's say it was a carbocation we're attacking, we're making a carbon-carbon single bond. We know that's super stable. As opposed to making some sort of ether with a conjugated double bond, like we've never seen that functional group before. Like the ether equivalent of an enol. That's not gonna be as, carbon oxygen bonds are not as strong, and carbon pi bonds are not as strong. So, in general, thermodynamic product, kinetic product.
And so there with the kinetic product, there would be an equilibrium where the electrophiles are popping back off the oxygen, right? Just
Exactly.
like an acid almost.
Depending on the temperature.
Right.
Right, you can basically lock it into the kinetic product if you do it at a low temperature.
Right.
You need your temperature high enough that these things can happen, but low enough that it can't get back.
Yeah.
Because for the most part, this is more stable than this.
Right.
So you're still downhill in energy.
Yeah.
And so if you do it at the right temperature, you can make the product without allowing it to come back. At high temperatures, you're always gonna make the thermodynamic product. It's gonna be favored because you give everything enough chance to settle into whatever's most stable.
And because then you're driving the oxygen attack backwards, both in terms of just now you have enough activation energy to move backwards and entropy.
Right. So it's a little bit like, you remember those, either you grew up with those little water toys where you push the button and it shot a jet of water and it like launched a little ring and you had to try and catch the ring on a little hook.
So my dad got one of those at Five Below a few days.
Do they really?
That's like training the rings and.
So getting the ring on there, once you get the ring on there, that's your kinetic product.
Then
It doesn't have enough energy to come back off of the ring, so it'll stay there. If you take it and you shake it though, you give everything enough kinetic energy to get where it needs to go, you wind up with a thermodynamic product, which is your rings on the bottom again.
that is
They
pretty.
still have those old things here.
I'm gonna get some of those next time we go on a road trip. No devices, you kids get these. That was my childhood.
Give them the classic ball and cup and just make them hate their lives. So it's like
Ball and cup. All right, let's take a break there. Let's go back in at 11. And we'll actually start looking at some of these reactions in more detail.
Jared, what's your mountain bike shop of choice?
Good. Getting tires, like starting to crack.
I mean, if it's just tired, it's just, I wouldn't go with sports games. No, so I so I would go, do you know, South Shore?
No, but
Go to South Shore.
okay, I'll do that.
Why? So. So check your poster. Like your mustache, man.
Oh, thank you, Mark. Good, thank you.
What? Yeah.
You did that research project. I think they're all PowerPoints, so you can't let you know it, right? You get a sense of it. I just have never used it. It's science, research project, poster. They'll have multiple sizes, they're already, and that's actually how, like, professional way, like, they're pretty poster, PowerPoint. Right, and then you send it to a workshop. And recommend it on my board. I mean, when it's digital, we don't actually print out in most unit sizes for extra. Like, usually the right proportions. I think that's those 365. Yeah, no worries. Yeah. Nice, nice. Yeah, absolutely. Obviously that, use the strong magnet, or we put. So why do we not read or ironically, the stern or just right, sort of like we use. But where's the guy there? But if like it is the Bible stuff, I would say that kind of like our best bet we can do. Right there. Well. Again, I'm no that's the. So, yeah, so, I appreciate it. Yeah, all right.
What sort of chaos are you guys getting up to in there?
I'm trying to attach a pencil to an apparatus hot glue.
Godspeed.
Thanks, man.
It's just like we were able to share evaluations and I tried to look at it yesterday and it's like 404, not found anymore. Yes, so and then some of like little, yeah.
Yeah, that's right. And we should look out for this. This is a need that part from here, yeah. Sweet. And yeah. You new tires, but you get, they have those too, they have like the added shirts. I have no idea where it's going, right? Yeah, they have like two side cracks and that's some sort of, those things. You know, that's behind the house. There's like a trail system that connects to little meadow, like parking airport, whatever is over there. Oh, yeah. So I went on like the tiny trail and the Gavia, that area. So it's like right at the end of the street with a little meadow. Yeah, a little trail going through the connects to but pretty amazing how many trails there are. It's like, that's a lot of awesome. Definitely gonna miss that when I go to Vegas. Yeah, for sure. Honestly, I'll probably be too busy at Vegas. Exactly. Just make sure you have some sort of.
Something activity where you're allowing the brain to rest and getting endorphins and lower the cortisol.
Best tactic that I had for that during undergrad and grad school was making sure that my friend group also did similar active things.
Yeah.
Because then at least if you're blowing off your homework to go do something, it's not just to go to the bars and go drinking, at least it's like, I'm gonna go rock climbing, or we went to the weight room a lot when I was in grad school. We'd hit like 1:30 in the afternoon, everybody would be fed up with their data and we just go lift weights for a couple hours.
Yeah, that's a good thing to do.
At least we were procrastinating, but at least it was productive procrastination, it's healthy procrastination.
Exactly, yeah, that's, I second that. Yeah, don't get friends who all they wanna do is go get hammered all the time.
Yeah, stay away from the business majors.
Yeah. Pre-meds.
Pre-meds tend to at least have a decent work ethic.
They do.
They have a decent work ethic, but yes, sometimes they're
They're also just like tend to be the most antisocial, which is hilarious when you think about
It's
it.
competitive with each other.
that's the most things with each other, and then they're
That's just super obnoxious.
they're really kids.
Yeah,
Yeah. Like a giant that crowd.
my roommates, my last year in undergrad was pre-med student who wasn't competitive and didn't get into med school as a result.
Yeah.
Because we drank too much. An athletic training major, an art major, and me. And then my now wife and girlfriend was an honorary roommate because she spent more time in art than hers. So, and she was a bio major.
Amazing.
So we had a wide range, but we weren't competitive with each other in general. Anyway, we only get, for this molecule, there's just more practice. We only get one enolate ion with two resonance structures. So try drawing it. Alright, so. Obviously, if our, maybe not obviously, shouldn't phrase it that way, but as you may have realized. If we have a quaternary carbon
Yeah.
on one of our alpha carbons,
Like, oh, you get it, 'cause you're.
we can't turn a quaternary carbon into an enolate. Because we don't have a hydrogen to lose. So if we don't have a hydrogen to lose, we don't need to worry about that carbon. Our tertiary carbon on the other side. Is where we're gonna see. Our enolate form. Then what's our other resonance structure then? It's gonna put the. Negative charge here. Right, so, and then once we make this, though. We can just treat it for the most part like it's any other nucleophile. We do have to consider that ambidentate aspect of it. In terms of which products we're gonna make.
In this one, I feel like stairs would play a significant role.
Stairs would play a significant role, so we might favor making the oxygen adduct. So a lot of times, remember that term adduct means that the addition product. The adduct that we would favor might be the oxygen one, just because of the sterics. Then again, this oxygen is still gonna be pretty sterically hindered too, between the two methyls here and this whole.
And the carbon would be accessed like orthogonal to the plane.
Right.
More or less.
But yeah, remember, these aren't gonna be totally planar, like benzene rings, they are gonna be in some sort of like. Double chair of love seat configuration.
You should trademark that.
So if we wanna actually make these, we can actually look at the pKa values. Because basically all we need to make these enolates is we need a strong enough base. That it can pull the hydrogen off of the alpha carbon. So depending on the actual conditions of the alpha carbon. That actually changes what base we could use, so acetone. Is not that acidic, it's a lot more acidic than usually the normal carbon hydrogen bonds. But it doesn't have. Much in the way of resonance to stabilize it, it just has that one resonance structure. Acetophenone. Almost 10 times more acidic. The whole pH unit more acidic. And then if it's an alpha carbon of an aldehyde. We actually get it all the way down to 16.7.
Wow.
So aldehyde alpha carbons are actually fairly acidic. To the point where you could use, I mean, the pKa of hydroxide is right around 16 as well. So you could get a decent amount of product just using hydroxide if it's an aldehyde.
Excited, and now I can like summon about it.
If you try to use hydroxide on acetone. You'll get some amount of it, but remember, this is a factor of 10, right?
Right.
So. Call it 16.2, 15.2, that's gonna be a difference of 10 to the. I can't even do subtraction right now, 10 to the 4th is favoring the acetone versus the enolate. Right, and so here's another common base ethoxide, pKa of 15.9 versus 19.2. So you make some of the enolate enough that you can have the enolate act as a reactant, but the trouble with that is if we have this equilibrium system and we want the enolate to be our nucleophile, we have to compete with the ethoxide, and the ethoxide is a pretty good nucleophile itself. Right, so that's definitely And if we do have this equilibrium system, if we have acetone and we have the enolate form of acetone, if they're both present at the same time. That actually is gonna give us a weird little side reaction. Because the ketone is an electrophile, it's got a partial positive on that carbon, right? The enolate is a nucleophile. What would the product look like if the enolate reacted with the acetone? It's something that looks like that, or the oxygen even attaching. Right, so that's gonna give us. Some sort of weird diamond structure. Which then, if we're under basic conditions, we actually can deprotonate it here. This is gonna have a resonance structure if we do that, we can actually wind up making something that looks kind of like this one. Right, so if we want to irreversibly convert ketones to enolates, we're gonna go back to Le Chatelier's principle again. If we make a product that leaves as a gas, we can take what was an equilibrium reaction and make it irreversible. Right, so basically, if you put a hydride source with a ketone or something that has an acidic alpha carbon, we can wind up making the enolate just by using sodium hydride. Typically, we use sodium hydride, we don't use just any hydride source, because what other side reaction is gonna happen? If we, what's another hydride source we could use besides sodium hydride?
Lithium aluminum hydride.
What happens when you expose a carbonyl to lithium aluminum hydride? You just reduce the carbonyl. So we need a hydride that's basic, but not a reducing agent. And so this just goes back to the way that they kind of like through trial and error over, the last 150 years, they've kind of settled into this hydride source works for that, but not over here. And to that aspect, okay, I'm like can't get around, there is some amount of memorizing.
So, yeah, just sodium hydride is the one that works.
Sodium hydride's the one that works. Sterically hindered strong bases can also work.
Okay.
But again, they need to be sterically hindered so that they don't just act as a nucleophile. So lithium diisopropylamide, also called LDA, which we used back, well, that was one of our sterically hindered bases when we were first talking about our Zapsa versus Hoffman products. LDA was one of our sterically hindered bases that would act as a base but not as a nucleophile. And that would give us the Hoffman product. And it has the added benefit of being an exceptionally strong base. So even though technically this is an equilibrium reaction, you look at the difference in the pKa values, we're talking about a difference of more than 15. We can essentially say that that goes to completion. It's gonna give us an equilibrium constant of 10 to 15, so call it going to completion. And here, we're making a hydrogen gas, which then we can just remove from the system. Right, so here's our two possibilities. we can use just a regular base, hydroxide or alkoxide. But that's gonna give us both products, the enolate and the ketone, which can lead to side reactions, which if we want that, it's fine. We just have to be aware of it. Or if we use sodium hydride or LDA, we get the irreversible enolate formation, so no side reaction, we don't get any ketone left over. And if we have a beta diketone, like that one we talked about earlier. That one, the alpha carbon right in between the two is so acidic, we don't actually need. We could just use sodium hydroxide in that case. So they just say LDA or sodium hydride is not even necessary to make it irreversible. Because at equilibrium, we favor the deprotonate, the enolate form. Because it's got two resonance structures to stabilize it. All right, some practice. Draw the enolate for A, B, C, and D. And then predict whether you would need to use. So, actually, I take it back. It just says use sodium ethoxide for all of these. And then tell me if that's makes the irreversible enolate, or if you're gonna still have some leftover ketone. So for A, we get that beta, the beta ketone. And so because it is on the beta carbon, that allows us to make the enolate irreversibly with just the sodium ethoxide. For B, it's still a diketone, but it's not a beta diketone. It's a gamma diketone, which means you're not going to get that same amount of resonance. So in this case, you'll wind up with both of these present. And then whatever weird fused dimer we get out of that as well. When this is going to react with that. Move that over, so we're gonna get some 2 rings, deprotonated alcohol, and a bunch of carbonyls all. We're gonna get a mess. The trick with those showing those dimer products is really just making sure you count your carbons. And that you didn't add a carbon or lose a carbon anywhere. So for C. It's gotta go on that alpha carbon because we don't have a hydrogen to lose on the benzene ring. It is resonance stabilized, but not by that much. So that one, you're gonna have, you'll probably, it'll be about a 50-50 mixture in this case. But you'll still have both versions. Then acetone we've already drawn. So definitely gonna have both versions of acetone, the enolate. Typically with these enolates, remember that they are present as resonance structures. We typically draw them just with a negative charge on the carbon because that's what's gonna give us a thermodynamic product. So that's that's not the more significant resonance structure, but it's the resonance structure that yields the most interesting product. On the right-hand side here, there's a predict the acidity from the names. So this is good practice for naming. So 2,4-dimethyl 3,5-heptanedione. 1, 2, 3, 4, 5, 6, 7. Three, 5, then 2,4-methyl versus 4,4-dimethyl. Which of these is going to be more acidic? And which alpha carbon is it? It's going to be more acidic.
I think the 2,4 because it can stand to lose a hydrogen on that one, or to both hydrogens.
Yeah, the one that the most acidic alpha carbon doesn't have a hydrogen on this version. So here, the only two alpha carbons that can make an enolate are 2 and 6. One hydrogen there, that's definitely going to give us better. The more acidic hydrogen, the easier hydrogen to remove. One, 2 cyclopentane-dione or 1, 3.
Just have them make pentanes, it'll just give you an easy drawing of the next state.
I need to practice on my pentagons anyway, as long as it's not a cycloheptane.
Right, those are.
The 1, 3.
1, 3. We don't have a beta. The only beta, we don't have a beta ketone. So that's not gonna work. I mean, it's still alpha carbons, they'll still be able to be deprotonated, but it's not as acidic. Acetophenone. Or benzaldehyde.
Definitely acetophenone.
Yeah, the benzaldehyde doesn't have an alpha carbon, an acidic alpha carbon at all. The only alpha carbon it has is part of the benzene ring. It doesn't even have a hydrogen. So the acetophenone by a long shot. We could look up what the acidity of an aldehyde is, but it's going to be, the pKa is going to be pretty high. This is why you don't trust.
It's in the record 17.
It's not the aldehyde.
Yeah,
Carbon, sorry, I'm waiting for the chemistry stat exchange. Although, I trust that more than Google. Uh, It's if you look up pKa of benzaldehyde, it gives you the pKa of the diol version, not of the acetal form. The pKa of the acetal form is 14.9, but the pKa of the aldehyde form is up in the 30s.
So the higher the benzene ring on there.
Mhm. I love finding a really good Stack Exchange thread where they come with receipts, give you all the citations and show their work.
And then there's Reddit.
And then there's Reddit, which it can be okay.
Yes, yeah.
The chemistry subreddits used to be really, really good. I haven't been on Reddit in a couple of years, but they used to be really trustworthy, or at least be able to see the argument back and forth more so than just, Google's AI spitting out an answer. All right, so what are some other reactions that can happen? So this is one that before they understood the mechanism, they were able to demonstrate that you could brominate the alpha carbon under acidic conditions. So with that in mind, they then figured out how enol formation worked. So if you know it's going through an enol intermediate, draw the mechanism. You don't have, unless you want the practice, you don't have to draw the mechanism for the enol formation. Since we've done that one a whole bunch today already.
That's just, formation and then addition.
It's enol formation and addition. We just haven't done addition for a minute, so
Yeah.
refresh your mind how acid catalyzed addition works.
Draw the acid catalyzed enol.
But it's gonna be a little bit different because our acid catalyzed addition was just HBr. And this actually needs bromine as opposed to just the bromide. So think about it for a second. Gen Chem students.
I'm redrawing the acid catalyzed enol formation mechanism.
Acid catalyzed, which we haven't done as much practice with, so. Like I said, it's not a bad idea to run yourself about it. Start with protonating the oxygen.
What is the proton transfer? When do you do the resonances?
Exactly. Once we get the enol. It's gonna look a little bit weird. Because our original acid catalyzed bromination was just HBr. To break this up, in this case, it actually requires the bromine, the diatomic bromine. But you're still just gonna have, you break the pi bonds. Trick is if we just drew it like that. We get an intermediate that looks like. Looks like this. Which we did draw a resonance structure that looks kind of like that, but a more stable form of it. Still gonna have a resonance structure here. It's just gonna look like this now. So then the last step.
And we are generating a bromide.
And we're gonna generate, we went with a bromide over here.
So would that just immediately react with the hydrogen to make HBr, because it's acidic, it's like we are making a negative thing, but it's just.
Right, well, in hydrobromic acid is a stronger acid than hydronium is. So you're actually not gonna make HBr. If there's water around, you're gonna make hydronium and bromide. But then that is just one last proton transfer. You can either show it as the bromide. Grabbing this, or just another hydronium. And that gives us our product. But if we're keeping track of how many hydrogen, this isn't the case of just being catalyzed by H plus. Because we started with hydronium. But then we made hydronium right away again, right? Because we had water act as the base for the first, or for the second proton transfer. And then we pulled another hydrogen back off, so we actually had a net gain in H plus. Right, because we made the HBr product or made hydronium as a product. And so that's actually what makes this qualify as being autocatalytic. So autocatalytic by definition just means that you're making the catalyst as part of the process, as part of the reaction. So in other words, autocatalytic reactions tend to speed up as they go. Because we're actually going to see a net increase in the acidity. Because we started with an H3O plus, but then we used it, but then we made it again. So that gets us back to the initial amount of H3O plus. And then we made more H3O plus at the end, so we actually had a net gain of one H3O plus. And that net gain is what makes it autocatalytic. Nice.
This one's, it was, I think the capture of this mechanism was just recognizing there were gonna be two places where there are resident structures that.
Right. And it's really, if you missed the second one, it's not too big of a deal.
Cause you can just show without that, like here.
Right, because if you just show, instead of just showing. They just showed it was one step. Your alkene bond broke to bond to the bromine at the same time as the oxygen dropped its lone pairs down, yeah. Really, the only time we need to show the minor resonance contributor as part of the mechanism is when that's the part, the resonance structure that actually does the reacting. This isn't the resonance structure that actually reacts. Because you need to have room for those electrons to move over. So because this is the resonance structure that actually does the reacting, it's important to show the resonance structure for this step. Here, it's not actually the resonance, it's the major contributor.
Yeah.
That actually does the reacting, so it's less important to show the resonance. It's important to recognize it's there. But as far as like getting full credit on the test. All right, so with that mechanism in mind, here's our last slide for the day. If the alpha carbons are asymmetric, the bromination will preferentially occur at the more substituted carbon.
Just because like they're going through that addition reaction with. You know.
We definitely wind up with a. It's a little contradictory to what we were thinking earlier, right?
Yeah.
But if you think about the enol product, a more substituted alkene is generally favored. So the more substituted alkene is generally favored thermodynamically, it becomes a thermodynamic versus kinetic issue. So generally speaking, though, those enols are uphill in energy enough that we're going to see the thermodynamic product once we go through the addition. So we're going to wind up with it going through it's basically the final thermodynamic product that's going to be favored is the one that goes to the more substituted enol. And then that allows us to put the bromine on the more substituted carbon. It's because of that intermediate for the addition step. As far as which enol is more present, our logic from earlier still makes sense. The problem is which of those two enols is going to be more reactive. Right. And that winds up being the more substituted enol is more reactive because it's less stable for the same reason that it was our major product. And so this enol is more favored, definitely it's the enolate, this is more favored. But this, because that transition state, when we do the addition, is gonna favor making this going from this one.
Just trying to.
Just because the carbon cation.
Because the carbon, yeah, remember,
Yeah.
it's Markovnikov's rule.
This one.
Yeah.
you add your bromine to the more substituted carbon, because that puts that intermediate or the substituted carbon. It's not, I guess I shouldn't say it is Markov-Lacoste rule, it's the same logic as Markov-Lacoste rule. This carbon is a more attractive, has more electron density. Because it has the electron attached to it.
Yeah. I guess what's kind of like not quite getting it 100% is the carbon's gonna have the positive charge on it, is the active. Carbon, the one that's
Right, but the partial negative is the one that's actually attacking the bromine.
Right.
That's why we have to have bromine and not just HBr, because we need a target for a nucleophile. And out of these, this one's more stable because it doesn't have the electron donating group, but this one's more reactive because it has the electron donating group. Remember, stability and reactivity are opposites, right? So more stable, more reactive, and more reactive means more product.
Yeah.
So it's the same logic we've been talking about, but it kind of gives us the opposite of our intuition because of that reactivity versus stability piece. All right,
And sorry.
no, we got time.
Where is the delta minus coming from?
It's coming from that resonance structure that looks like,
So I'm just thinking of like the acid catalyzed one, right? This and something like, I see the delta pluses.
each of these both have a resonance structure that looks like this,
Okay.
right? And then this one, it would be the other direction. So it'd still be.
Oh, yeah, okay.
This is more stable as a resonance structure than this one is. But that means if you make this, it's gonna be more reactive.
Okay, yep, cool. So it's just the resonance, just the two structures up there, just their resonance.
Yes.
Okay.
Cool. Thank you. That makes sense then.
All right. So there's your intro to alpha carbons. We'll do a couple more specifics. We'll spend some of the next set of slides focuses on those condensation reactions where the enolate reacts with the ketone itself. That's called a condensation reaction because you took two molecules and you turned them into one big molecule. So we'll talk about those condensation reactions next time. All right, do you guys want a quiz this weekend? I could make the argument either way. We're at the end of the series. We're going over stuff. Would be good to have some practice. Are you feeling pretty good about the material so far?
I'm feeling good about what we went over today, maybe quiz with acid derivatives, Michael.
Just do some repetition.
Yes,
Okay.
that's just so much.
Yeah. All right.
That might help a little bit.
There's a non-zero chance I will get it in on Monday morning.
That's fine. That's right. You're taking a quiz this weekend.